Okay, let's start. I still want to talk about the first set of homework problems and listen to y'all's ideas about them, or try to respond to questions about them. And then I think on Wednesday, though, that will be the day finally that we collect them. All right, so I still want to give you a little bit more time to process what we say in class about the problems, or come by my office and ask me questions about them as well. Okay. So remember, on a lot of these problems where it says show something, right? For those of you who have had proofs class, right, which may be most of you, you may be thinking that you want to write everything down, formally correct, rigorously correct, and that's great, but that's certainly acceptable. But you don't really have to, for our purposes, really explain things perfectly correctly, rigorously correctly, if you can sort of just explain your ideas, right, in a coherent way as to why you think, whatever you're instructed to show is true, right, and sort of give the reasoning behind that, then that's also fine, okay? So I don't want us to spend too much time, wrestling with the formalisms. It's more about, although sometimes that's important, it's more about, explaining one's sort of key insight into the problem, right? Or explaining why you think, or giving some justification about why something is true, right? Okay. All right. Okay, so, all right, well, I'm not sure how helpful that advice is, but there it is, okay. All right, but before we talk more about some of those problems, I want to try to finish up again, or get further into at least. Surely by Wednesday we'll be done. Our little tour of just different types of combinatorics problems, right? And last time we were talking about problems on grids, right? Rectangular grids, like chessboards. So, we started with chessboard problems, chessboard covering problems, and that's the subject of most of this homework, right? But in general, there are lots of ways to pose combinatorial type problems on rectangular arrays, and there are many famous examples of combinatorial problems based on those situations. So last time we looked at magic squares, right? And that's where you're trying to fill out an n by n rectangular array. Okay, this would be a 5 by 5, right? Rectangular array, right? Or you can call it a grid, or I guess you could call it a chessboard, right? A 5 by 5 chessboard, and you're trying to fill that in, right, with the consecutive integers 1 to n squared, because that's how many squares would be there. So here we were trying to fill in this rectangular array, right, with the integers 1 to 25, 1, 2, 3, 4, up to 25. Okay, and for a magic square, you do that in such a way that the rows and the sums and the diagonals, right, both diagonals all add up to the same number. Okay, that's called a magic square, and that's a famous puzzle from mathematical history. So last time we showed you this little famous technique for building magic squares. If you have an odd, if the n is odd, so if the number of rows and columns is odd, we showed a technique for doing that. But there are lots of ways of constructing magic squares. There's lots and lots of magic squares, right? Okay. All right. So another. So if you weren't here last time, you can look at the. You can look at the tape of the lecture online, learn more about magic squares. And again, they're just kind of a curiosity or a puzzle. Another sort of puzzle that slightly different type of puzzle, but also with a rectangular array of numbers. But these actually have more important applications, especially in experimental design. So, design of experiments. So, another type of grid is called a Latin square. So in a Latin square, again, you get an n by n grid, and you're going to fill that up. Not with all of the integers 1 to n squared like you do on a magic square, okay? But you fill up the rows and columns just with the numbers 1 to n. So, for instance, if you were building a 5 by 5 Latin square, okay, you would fill that up, all the squares, with the numbers 1, 2, 3, 4, and 5. So you're going to repeat values, right, okay, when you do that. But you want to do it in such a way that each row and each column, so all the rows and all of the columns, will contain all of these values, okay, right, 1 to whatever the order of the Latin square is, all right? So here's an example, simple example of a 4 by 4 Latin square, okay? So see, you're only filling it up with the numbers 1, 2, 3, 4, right, okay? But you want to do it in such a way that every row and every column contains all of those 4 values. Let's see, is this really 1? Okay, I just wrote this one down, so maybe it's not, right? So the first row has all 1, 2, 3, 4, right? The second one, the third one does, that one does too, right? And then, but you have to have the same thing in the columns, okay? So do all of these columns have, yeah, I think they do, right? Okay, so that's an example of a 4 by 4 Latin square, all right? Okay, so in a way, that seems like a little bit simpler puzzle to complete than a magic square, and in fact it is, okay? It's fairly easy to create, it's fairly easy there to create Latin squares, all right? So this is just an example of one, okay? So in fact, here's kind of our first problem here. Oh, by the way, a Latin square, I'm not sure if I'll mention this again, but it's kind of useful when you're trying to count all possible Latin squares. A Latin square is said to be reduced if the first row and the first column are in the correct numerical order, okay? But that's not a general requirement for a Latin square, all right? But if you have the first row and the first column in a numerical order, left to right and top to bottom, then that is said to be in reduced form, okay? So this is not in reduced form, all right? Because the first row is not in correct numerical order, right? And neither is the first column, okay? All right. So our first very basic question, right, that we might ask about Latin squares is if you're given a particular order, right? I mean, this is the combinatorics, it's supposed to be combinatorial type problems, right? So if you're given a particular order, right, you know, so this could be 1, 2, 3, right, in this case 4, we want to show that you can always produce a Latin square of that order, okay? So, so in a sense, Latin squares are kind of easy to create, right? Okay. So now, initially here, we're not going to talk about counting the number of Latin squares, all right? But just show that this set of Latin squares is non-empty, okay, for any particular order, all right? So we've already shown that's true for order 4, right? Because here's an example of a Latin square, all right? But can we come up with some general scheme for can we come up with some general scheme for creating Latin squares of just any order, all right? Let me let y'all experiment with that for just a second, okay? So let's try an easy one, okay? Let's try 3 by 3. Well, you might start with 2 by 2. I think 1 by 1 maybe is too easy, okay? All right. So what is a 1 by 1 Latin square going to look like? Yeah, that's right, okay. So when n is equal to 1, right, you get kind of a trivial, or definitely a trivial Latin square, right? Okay, all right. So you might try here just building one for 2 by 2. That can't be too hard either, right? If one exists, okay. And then maybe slightly trickier there is 3 by 3. So just try creating, 2 by 2. That will be easy, or just a 3 by 3 there, Latin square. Okay, so Kaylee's going to start. While y'all are playing with that, Kaylee's going to pass out the roll, right? Okay. So remember to sign in your slot from last time. So if you've forgotten your number, I attached the roll from last time, so you'll know where you signed. If you're new, though, you will start with 17, okay? So we had people here up to 16 last time. So if you're new, start with 17, and then, sign in the next available slot. And, of course, remember your number, and you're going to sign there every time, right? Okay? Okay. All right, so y'all already find a 2 by 2 and or a 3 by 3. Latin square. Is that so simple that you could almost just write one down at random? Okay, yeah, all right. Yeah, it's not really hard to find, I think, especially small Latin squares. What is the 2 by 2? Is there only one? There's 2 possible ones, okay. What about in reduced form? Is there one in reduced form? So that would be what? 1, 2, I guess we'd have to put a 2 here if it's in reduced form here, right? And then our only other choice there would be 1. But that is a Latin square, right? Okay, because again, every row and every column, right, has all of those numbers 1 to 2, right? What's the only other possibility? 2, 1, and 1, 2? Yeah, so if we put the 2 there, right, the 1's got to go here, the 1's got to go here, and then you only have a 2. So I guess that would be it, right? Only 2 possible Latin squares there of order 2. Oh, that's cool, right? So, well, at least we enumerated this set L, right? Okay, our grand goal in this course, right, is to try to count these finite sets, right, like L. And so, at least in the case when n is equal to 2, right, we know that not only is the cardinality of L greater than 0, so L is not empty, right, but now we know that L, in fact, has 2 elements. And we did that just by exhausting the possibilities, right? Okay, so at least initially here in the class, that's sort of been our counting technique, right, is just try to run through all of the possibilities, okay? In this case, there weren't very many possibilities, so that was pretty easy, all right? What about 3 by 3? I have no idea how many of these there are, but so let's see, can we get one in reduced form? Did y'all find one in reduced form? So there's how it's got to start, right, if there is one. And can I complete this? That just means I have to fill in these 4 squares, so that must not be too bad, right? Can I put a 1 here? Oh, no, right? Okay, because that's going to force this to be a 3, correct? Okay, and that's going to mess up the last column, so that was bad. All right, so I guess what do I have to do? Put a 3 here? And then that means I have to have a 1 here, right? Okay, and then that means this has to be a 1, and that means that this has to be a 2? Is that a Latin square, though? Yeah, okay, that works, right? Okay, so, all right, so that's it, all right? So I think in reduced form, I think there's only 1, right? Okay, because I don't think there was any other way to complete that. Was there any other way to complete that? I don't think so, right? I had to have the 3 there, right? And then that forces a 1 here, and then these are sort of forced, right? Okay, so at least in reduced form, right, there's only 1 Latin square, 3 by 3, but that's enough to mean that this set is not empty, correct? Okay, so I'm not quite exactly sure how many there would be altogether. Seems like we might be able to count those, though, because just by exhaustion, right? Just by exhausting all of the possibilities. Okay, well, so pretty easy there also to find 3 by 3. Okay, all right, so look, if you're in general, let me see if this works, but I didn't test this, so so if this doesn't work, y'all are going to have to, we're going to have to look for something else, okay? So let's imagine that we just have n rows and n columns, okay? So I'm trying to put some ellipses here to indicate that, right, that have a variable number of columns there and a variable number of rows, correct? Okay, so let's imagine now, so there's again, n rows there and n columns, and I'm trying to build a Latin square in general. So let's just imagine that the first column is in reduced form, but I'm not going to worry about the first row, okay? So I'm just going to put the first column in reduced form. So I would have 1 and then 2, right, and then et cetera here up to that last entry there in the first column would be n, okay? So here's my scheme, and let's see if this works. So what I'm going to do is shift the numbers, all right, okay? So I'm going to shift the numbers. Well, I was pointing up, but let's think of shifting the numbers down. This is to fill in the second column, okay? So to fill in the second column, I'm going to shift the values down. Now, obviously, I cannot shift the n outside of the Latin square, correct? So I can't shift it down. So I'll have to wrap that one back around, okay? So see how I'm going to do that? So then this would be n, right? Okay? And then here would be 1, and I guess what would be in this thing? That's n minus 1, correct? Okay? And then I'm just going to keep doing that, okay? Now, until I think, run out of shifts, okay? And so this would have what would be up here then? Say, for instance, in the third column. Yeah, then you would have n minus 1. What's this one going to be? N, right? And then down here is n minus 2, right? Okay. What does the last column get filled in with? It starts off with a 2. Is that right? Okay. And then what's at the end here? What? 1? 1 goes down there. Right. Okay. Because when you make all possible shifts, right, the 1 travels to the last row, right? Okay, and notice how many shifts possible then is that's n, right? Okay, so so you fill in all of the columns. Are those? Is that work now? Well, all of the columns are correct. I know, right? Because they're just shifts of that first column, which had all n of the numbers in it. What about the rows, though? Do they work? This one definitely works, right? Okay. Yeah, they all work, right? Okay, so I think there's an easy way, right, to construct a Latin square for any value of n. Okay, so it's pretty easy, pretty trivial there to build Latin squares. Okay, it's not a mystery. So usually when we are working with Latin squares, we like to make the problem a little bit more difficult. So we'll put some additional restrictions on the Latin square to make the a little bit more fun to think about creating a Latin square. So we want a Latin square with some additional properties, okay, that makes them a little bit harder to create. All right. Okay, so let me show you some famous variations on these Latin square type of problems. But before I do that, I wanted to get y'all to try to look for me. So if you have your smartphone, try looking on Google for Latin square, okay, and see if what's known about the number of Latin squares, okay, for a particular order. All right. So do we know anything actually about the cardinality of this set, okay, for a particular value of n. Okay, it was certainly easy to create a Latin square, right, for any order. So that sort of implies that there may be lots of these, right? Okay, so try Googling Latin square and see if anything's known about the cardinality of L. By the way, we thought for 2 the cardinality was 2, correct? All right, let's see if Google confirms that. Oh, wait, see, I have this on my phone already, so it's pretty easy to find. Let's see if we were correct. Oh, it looks like we were. Yay! Anybody find anything yet? What was the first thing that came up when you were looking for that? What did you find, Kaylee?
Wikipedia.
Yeah, the Wikipedia article is pretty good, so I would look at that one, okay, and scroll down there and see if you can find anything in the Wikipedia article about Latin squares, okay. It does mention where the term Latin comes from, and it has nothing to do with ancient Rome, right? So. Did y'all find any numbers there?
I found one for reduced
Mm-hmm.
squares.
Mm-hmm.
It gets really high.
It gets really high really fast, right? What is it for 2 there, Dalton? What does it say for reduced Latin squares?
For 1 through 4, I think there's only one because it doesn't have a number for those.
Not quite.
Okay, 4 is 4.
Yeah, okay. Yeah, so 4, yeah, so the number of reduced Latin squares for order 4 is 4. For 3, it's 1. I think we'd already discovered that, right? And for 2, it's, of course, it's also just 1, right? But the number of Latin squares altogether,
1, 2, 12.
yeah, is 2 for 2. We knew that, right? For 3, it's actually 12. So you can find 12 Latin squares of order 3. For 4, it starts really getting big. So for 4, it's 576 already, okay? And that's not reduced. That's just in general Latin squares. And for 7 already, wow, let me see if I can even write down this number, okay? So for 7, it's, wow, 61 something, okay? Yeah. So, so something is known. Yeah, I don't know what that, I don't even know how to read that off. That's trillion, right?
Yep.
61 trillion, 479 billion, 419 million, 904,000. Exactly, okay? So lots of already, wow, lots of Latin squares of even order 7. So, wow, so if I had all of you build a Latin square of order 7, probably almost everyone would have come up with a different Latin square, right? Okay, because there are just so many possibilities there. There are actually formulas known. If you read that Wikipedia article, it'll say there are actually formulas known for the number of Latin squares, but the formulas are very difficult to compute, okay? They're very difficult to program and compute because of the size of the number of Latin squares. That makes even the formulas difficult to use, okay, because the numbers get extremely large, okay? Really fast. All right, so just lots and lots there of Latin squares. All right, so again, to make the question more interesting, right, of finding a Latin square or counting Latin squares. Again, there are lots of variations on these problems. So here's the most famous variation. And again, this is a variation that has actually important applications in design of experiments in statistics. All right. So this problem is due to Euler, who is from the 1700s, who's responsible for lots of combinatorial puzzles. Okay. He's one of the fathers of combinatorics. All right. So although Euler did not completely solve this problem. All right. So here is Euler's question. All right, so it doesn't start off as a Latin square question, but we'll rearrange it as a Latin square question. So suppose we have 36 officers, okay? So this is going to be a very military type statement of a problem here. So we've got 36 officers, and they're drawn from 6 different ranks, okay, of officers, right, okay, and from 6 regiments, okay? So 6 ranks and 6 regiments. of the 36 officers. So what that means is that no two officers are going to be from the same regiment or have the same rank. Okay, so you have sort of 36 distinct officers here, right? Okay, of different ranks and different regiments. Okay. Now, what we want to do is to arrange the officers into a drill formation. Okay. So we want to put them in a 6x6 drill formation. In other words, we're going to arrange them into a 6x6 array, but we want to do it in such a way that each rank and each regiment, okay, each rank and each regiment is represented in every row, okay, and every column of the drill formation, okay. So we're going to line them up a 6x6 drill formation, but we want it in such a way that in every row of the formation, all the ranks are represented, okay, but also all the regiments are represented in every row. But to make it more difficult, we also want the same for every column in the drill formation. So we want every rank and every regiment represented, okay, in each column, all right? So Euler really just wanted to know, is that even possible to do that? Okay, so can one build such an array? Okay, I mean you have enough you have enough officers, right, to create the array. Okay, because you've got 36 officers, right, and if you build a 6x6 array, that's going to be 36 positions. So you can put them into a 6x6 drill formation, but can you do it in with those extra restrictions, right? That every rank must be in every row. Every rank must be in every column, but similarly, every regiment must be represented in every row, and every regiment must be represented in every column. So a completely diverse drill formation. Okay. All right. Now, to analyze the problem a little bit, let's back up, okay? Because Euler's famous problem is posed with 6 regiments and 6 ranks, so 36 officers. But let's see if we can do and by the way, that problem is called the problem of the 36 officers, okay? But let's see if we can just think about the problem of the 9 officers, okay? So let's cut it down a little bit by half, actually. Let's suppose we have 3 different ranks, okay, and 3 different regiments, and let's see if we can arrange them in such an array, okay. So let's see if we can think about the problem of the 9 officers, okay, as opposed to the 36 officers. All right, so to make this a little bit more concrete, since we're just talking about soldiers in our mind here, right? Let's actually write down the soldiers, okay, on paper, okay, so we can have something to work with. So the way I'm going to represent a soldier is by an ordered pair, okay, and that ordered pair, of course, is going to correspond to the soldier's rank. I'm going to put that first, but you can do it backwards, right? So rank is going to go first, and then regiment will be second, okay? So the first person on the list is of whatever rank I'm labeling 1, okay? And then he's of whatever regiment I've labeled 1. I'm going to that's pretty clear, right? I'm going to label the ranks by 1, 2, 3, and I'm going to label the regiments also by 1, 2, 3, okay? If you want to be more in the spirit of the problem, you can think of 3 ranks. What are 3 ranks? I don't even know. Colonel, general, lieutenant, maybe, okay, right? I have no idea how regiments are named, okay? But in any event, all right, we'll just number them. So this officer is rank 1, regiment 1, right? This is rank 2, right? Regiment 1, so forth. So I guess I put everybody from the 1st regiment first here in this list. and then this is rank 1, but regiment 2, and so on and so forth down to the last person here is, what is that, rank 3 and regiment 3. So, of course, how many ordered pairs do I have there? 9, of course, that's the 9 officers, correct, okay? And see, what we want to do, Eduardo, is arrange them in a marching formation, 3x3 marching formation, again, right, so that I have all of the, as I mentioned, right, all the ranks in every column, all the regiments in every column, all the ranks in every row, all the regiments in every row, okay? So if we just do this naively, let's just see what happens. So I'm just going to, just the way I wrote them down there, let's just start filling in a marching formation, okay? So it's easy to create the marching formation, but, probably it's not likely, right, we're going to have the arrangement that we were looking for, right? So I just wrote them out, just filling up the rows first, okay? I just put them into the marching formation, okay, like this, okay, and obviously does that meet my the conditions that I was looking for? Well, look, what you can, of course, to check this, right, just simply sort of pull apart, right, okay, this array of ordered pairs. So I'm going to first pull off the ranks, okay, into a 3x3 array, and then I'm going to pull out here the regiments into a 3x3 array, right? Okay, and I need to have all of the ranks in every column and row, and I need to have all the regiments in every column and row. And obviously, has that happened? No, I missed by a long shot there, right? Okay, so I've done a terrible job of arranging this particular formation, okay? Notice that in a solution to the problem, right, okay, in a solution to the problem, what should these two squares end up being? Those should be Latin squares, that's right, okay? So those should end up being Latin squares, correct, okay? Because, remember, this is this is kind of the square of, what were these, the ranks, right, okay? These are the square of the ranks, and remember, I've got to have every rank represented in every row and every column, right? So that should be a Latin square, and this also should be a Latin square. Did I do this? Yeah, I did. Did I do this correctly? Did I break this up right? 3, 2, 2, 1, 1. Yeah, right. Okay, so I did pull it apart correctly, but those aren't Latin squares, right? Okay. What we're looking for, right, in to solve this problem is we're looking for 2 Latin squares, right? So I want 2 Latin squares so that when I superimpose them, so I'm looking for 2 Latin squares. These are not Latin squares, right? But what I'm hoping for are 2 Latin squares so that when I superimpose them, what happens? What now?
When you superimpose the 2 Latin squares, you'll have the system one where there's a rank and regiment in every row.
Well, yeah, right. So, yeah, when I superimpose so I have 2 Latin squares, but so Dalton, if I have 2 Latin squares, I will have every rank, right, in every row and column, and I will have every regiment in every row and column, right, okay? Because this is the rank Latin squares and this is the regiment Latin squares, right? Okay. Every ordered pair would be there. That's right, right? Okay, I would have every possible ordered pair, okay, once I superimpose the 2 Latin squares, okay? Every ordered pair that you get by taking numbers 1, 2, 3 and matching them with numbers 1, 2, 3, right, okay? Such Latin squares are called orthogonal to one another, okay? So if you have 2 different Latin squares, so that when you superimpose them, you get every possible 2x2 ordered pair, right? You're going to have what are called orthogonal Latin squares. So this was the rank, right? And this was the regiment. I didn't label that before, okay? So there's just the description of orthogonal Latin pairs. That's just what I just mentioned. Okay, so if you have an n by n, a pair of n by n Latin squares, right? Okay. If you superimpose them and you get every possible ordered pair built from the numbers 1, 2, 3 up to n, okay, then you have orthogonal Latin squares. So Euler was really looking for a couple of orthogonal Latin squares of what order? 6, right, okay. That is the solution to the 36 officers problem, okay? We're looking for 3 by 3, okay, Latin squares, right, okay, orthogonal Latin squares to solve the 9 officer problem. All right, y'all. I want y'all to try this one. Okay, so let's cut it down even easier than the 9 officer problem. Let's look at the 4 officer problem. Okay, so show that there are no orthogonal Latin squares of order 2. All right, so you cannot have a pair of orthogonal Latin squares of order 2. There aren't that many possibilities, right? Because how many Latin squares of order 2 were there anyway? There were only 2, right? Okay. So if you have orthogonal Latin squares of order 2, you got to have some combination of just those 2 Latin squares, right? Okay. That's not going to be many possibilities, correct? So see if you can just quickly demonstrate there, right? Why there's no orthogonal Latin squares, right, of order 2. By the way, if you have orthogonal Latin squares, I guess it's not really strictly required that the Latin squares be different, but do they have to be? I'm not sure. I didn't think about that. Okay, what are our 2 Latin squares of order 2? 1, 2, 2, 1, 2, 1. Yeah, 1, 2. What is it? 2, 1, and then just the opposite of that, right? 2, 1, 1, 2. Okay, so. That shouldn't take long, right? Did y'all try putting those together? So remember, what you want to do there is just superimpose those, right? Right, Shelby? I can see that's what you're doing, okay? And see if you get every possible ordered pair represented, right, in when you superimpose them. Does that happen if we just superimpose these 2? So what happens if we just combine those 2? What do we get? What, we get 1, 2, right? Am I doing this right? 2, 1. That is a different officer now, right? Okay. And then here we get what? Yeah, we get 2, 1 again. So that can't happen, right? Because that officer has to be in 2 places at once. So not going to work, right? Okay. So in that order, it's not going to work. I guess in the other order either, right? What if you try just with itself? Does that make any sense at all? So suppose I just try this one with itself. What goes wrong there? You get 1, 1, 2, 2. Oh, 2, 2 again, right? Okay, so yeah, that doesn't work either, right? So. Okay, so I think that's pretty obvious, right, that we're not going to have, of order 2, right, we don't have orthogonal Latin squares, so we cannot solve the 4 officer problem, okay? All right, now here's what Euler did know. Euler knew if you had if n was an even number, let me take the easier situation. If n was odd, Okay, if n is odd. So 3 by 3, 5 by 5, 7 by 7, those orders all have solutions. So you do have orthogonal Latin squares if n is odd. And Euler showed how to construct that. So we do have a solution to the 9-officer problem. Okay, there is a solution to the 9-officer problem. Not sure what that is, okay, but there is one. And I guess the 49-officer problem would have a solution as well, 7 by 7, or the 81-officer problem would also have a solution, okay? All right, now Euler also showed if you have an even order, but it has to be an even number that's a multiple of 4, okay? So if you have an even number that's a multiple of 4, you also have a solution, which Euler demonstrated. Okay, so let's see. So what numbers would that include? 4, 8, 12, right? Okay, 16. We know there is no solution for 2. We just showed that, correct? But 4 does have a solution. So the 16-officer problem has a solution. And then what's the next one there? 8. So the 64-officer problem has a solution. Notice what's missing there, though. The problem that Euler actually stated, which was 6. Okay, right? That is an even number, but not a multiple of 4. Okay? And Euler did not know the answer to this question. Okay? So he posed that as a puzzle, and that was a famous puzzle due to Euler. That was there was no solution to that for a long, long time. Okay? So, and it wasn't until 1900, okay, that it was demonstrated that there is no pair of orthogonal Latin squares of order 6. Okay, and forgot the person that did that, but he did it by exhausting possibilities. So it was a difficult thing to demonstrate. Okay, he just sort of figured out what all the possible orthogonal Latin squares of order 6 would be, and demonstrated that none of those would work. Okay, but actually Euler had already conjectured that there was no solution to the 36-officer problem, but he didn't know that, and he actually claimed that there's no solution to there's no pair of orthogonal Latin squares for any order that's a multiple of 4. Okay, including 6. I'm sorry, that's not a multiple of 4. So any even order that's not a multiple of 4, he said, I think there's no solution to this. So that includes 6. So he was right about 6, but he's wrong about, for instance, what's the next one? 10. Okay, he's wrong about that. All right, because actually there are orthogonal Latin squares for actually any order other than 2 and 6. Okay, those are the only two for which we don't have orthogonal Latin squares. That was not known, though. That was not demonstrated until 1960. So that took a long time to solve that problem. But for any other order other than 2 and 6, you can find orthogonal Latin squares. Okay. So I think it may be one of your homework problems there to show that this has a solution. Okay, so see if you can find for order 3 a pair of orthogonal Latin squares. Anybody found one already? Oh, Dalton says he already has one. We'll see. One of your homework problems is done, Dalton. So, all right, so you're done. Okay, nice. All right, that's one variation on Latin squares. Here's another one that you're probably more familiar with, other than the 36-officer problem, although that one has important applications. Now, I don't know how important the applications are of this famous version of Latin square problem, but other than the one that we're going to see here. Okay, so y'all are all familiar with Sudoku puzzles, right? Do y'all play those sometimes? Okay. All right. So now, okay, so you're going to have to help me because I don't play Sudoku at all, right? And I was always confused about the rules here. So so how does this work? So what happens in a Sudoku puzzle, now usually it does start like this, right, okay? That's just sort of the grid for a Sudoku puzzle, but it starts with something like this, correct, okay? Where you've got some of the values filled in, right, okay? And so what's the goal, though? That I don't know.
It's like a Latin square.
It is a Latin square, okay?
But there are individual boxes within the Latin square where you also have to have all 9 digits in each box.
Right, that's right. So it's kind of a Latin square with just an additional condition, right? Okay. So in a Latin square, right, you've got to have all of the. So this is a 9 by 9 grid, right? Okay. So you would have to have all of the integers 1 to 9, right, represented in. Is it every row and every column? So you do have a Latin square. So it's building a Latin square, but you also have the grid subdivided into a slightly different way, right? Okay, so normally the way you think of a grid being subdivided is with rows and columns, right? Okay, and each row and each column would have 9 boxes in it, right? Okay, so if you think of the rows as being a subdivision, you have 9 rows, each with 9 boxes. But because you have a square grid, there are other ways other than rows or alternatively columns to break the grid up into collections of 9 boxes. Okay, but if you break it up into collections of 9 boxes, how many of those collections do you need? You need 9 of them, right? Because you've got to have all 81 boxes accounted for. So in a Sudoku puzzle, so the additional way you're going to break up the grid into a collection of 9 boxes is with these little sort of sub-rectangles, right? Okay, each one of which is 3 by 3, and therefore has 9 boxes, right? Okay. So one way of breaking up the grid is to, for instance, by columns, right, where you have 9 boxes in rows, where you have 9 boxes in each row, correct, right? And you've got 9 of those rows. Well, in a Sudoku puzzle, you also break them up into these little sub-rectangles, right? Each one of which has 9 boxes in it. So therefore, there are 9 of those sub-rectangles. And each one of those also has to contain all 9 of the digits, right? Okay. So you've got this extra additional condition on a Sudoku puzzle, right? And then, but the way the game is played, right, is some of the numbers are filled in, and you have to. So sort of the puzzle is partially solved, right? The Latin square is partially created, and you have to. You have to fill in the additional boxes. Okay. All right. Now, so that's another variation on Latin square problems, just to make them a little bit more interesting than just building a normal Latin square. Okay. Yeah.
Do you have to do any of those for our homework?
Is there a Sudoku problem in the homework? Oh, there is. Okay. All right. So. Okay, so for those of us who don't do Sudoku puzzles, that might be a challenge, okay? You want me to make it harder? Yes. Yeah, okay. All right, well, no, this is just... Sudoku problems are one example of a more general type of problem called, I think it's Goretzky design, all right? So you don't have to, if you have a square array, you do not have to break it up into sub-rectangles, okay? You can break it up into other collections of boxes, okay? So here's an example, but it's a very simple example. So here we have a 4 by 4 grid, okay? A 4 by 4 grid. And so, of course, you can break it up into rows, right? Each row would have 4 boxes in it, and then you would have 4 of those rows, correct? Or you could think of that vice versa as columns. Or in a Sudoku puzzle, right, we would break that up in a Sudoku puzzle. Let me see if I can find something to point with. In a Sudoku puzzle, right, we would break that up into 4 sub squares here, right? Okay, one here, one here, one here, and one here. And then when we filled it in, we would want all of the all of the four integers, right, to be in every row, every column, and then each of the subsquares. But you can also break the a rectangle up, the original array, into other collections of four boxes, and that is called the Goretti design. So here's another example of breaking that up into collections of four boxes. In this case, they're all L-shaped. All right. So the way the book has demonstrated that cutely there is by putting, these what are those called, suits? By putting these card deck suits here, right? So there's one of the collection of four boxes, right? There's one, and then here's one, and then here's another one, right? Okay. And so, but you can also play Sudoku with this puzzle. Okay. So you can build a Latin square, or you can ask at least to build a Latin square so that all of those four collections there also have all of the integers 1 to 4 in them. Okay.
That's usually still doing the rows and columns as well.
What now?
That's usually still obeying the rules and columns rule as well.
It's still a Latin square. That's right. So still a Latin square, right? So you'd still want a 4 by 4 Latin square, of which there are how many? Forgot. Did we count that? 12?
12, yeah.
So there aren't that many Latin squares to start with, right? Was it 12 or was it 576? Oh, 570. Okay, all right. So there are plenty of them. Okay, so all right. So there are So there are 576, right? So build one of those 576 Latin squares, right? But in such a way that you get 1, 2, 3, 4 in the in the clubs place, right? 1, 2, 3, 4 in the spades boxes. 1, 2, 3, 4 in the diamonds boxes, and 1, 2, 3, 4 also in the hearts boxes. All right. Is that a solution to that? Yeah. Okay. So the book demonstrates a solution to that version, okay, of the problem. So I have the book doesn't mention this. So I have no idea if you're guaranteed for any way of breaking up the original array into sub-collections. Are you guaranteed that you can build a Latin square that satisfies the puzzle? Okay. Oh, I don't know. All right. So we could research that. All right, so there's some famous combinatorial problems built on grids. Okay, built on grids. All right. Okay, before we talk about the homework, let me at least start the next notes, and I'll let y'all think about them because the first problem is kind of easy to. Introduce. So another really great setting for combinatorial type problems is, surprisingly, you wouldn't think so, all right, but is geometry, all right? So there are many combinatorial type problems that are stated in a geometric setting, lots and lots of them, okay, and they're really fascinating problems often. Okay, and so let me give you just one example. Okay, and it kind of illustrates a counting principle that's going to be important to us a little bit later in the course. One of your homework problems does as well. So this is going to reinforce one of your homework problems. All right, so here is a geometry problem, or at least it's stated as a geometry problem because it has to do with straight lines. I mean, what's more fundamental to geometry than straight lines, right? Okay, and so let me give you the problem. So suppose you have some collection of lines. Of course, they're drawn in their lines. So we're going to keep them on a two-dimensional surface. We're not going to draw them in three-dimensional space because that's really hard to think about. All right. But suppose we have some lines drawn on a two-dimensional surface, and now we're going to insist that they're drawn in general position. Because if they're not drawn in general position, then the way the lines can interact with each other gets very complicated, okay? So that becomes its own problem. But in general position just means that no two of the lines are parallel, so we don't want the lines to be parallel because that's going to mess things up. And no three of the lines will intersect in a point. Now, if the lines are not parallel, every pair of lines is going to intersect, right? Okay, so you have lots of intersection points, but you don't have a situation where three lines cross in the same point, okay? So any place two lines intersect, it's only two lines that intersect at that given point. That's called general position. That makes the problem much easier to analyze, okay? All All right, so that's the situation. So we've thrown some lines on the plane. They're not parallel, and we don't have three of them or more crossing in a single point. All right, now, of course, when you draw lines on the plane, what happens to the plane? It gets subdivided into regions, correct? Okay, right? When you draw one line, for instance, what does that do with the plane? It breaks it into how many pieces there? Two, right? Okay, something to the left and something to the right, or you can think of something above and something below, right? Okay, however you think of the line as being oriented, right? Okay, yeah. So when you draw these in lines, by the way, we can make this totally vacuous and say we're going to draw zero lines, which leaves how many regions in the plane? One, right? Okay. All right. But anyway, once we draw these lines, it's going to break the plane up into several regions. What I want to know is how many. Okay. So when you draw lines in this general position, how many regions will that break the plane up into? Okay. All right. Let's experiment with this a little bit. Okay. Now, do y'all have your homework that I? Oh, who wasn't here last time and did not get the homework? Did y'all get on the roll? Did y'all put your name on the roll? Yeah, okay. All right, oops. So I know some people did not sign the roll. Okay, so let's get it to the people that did not sign the roll. Anybody else needs one? So I've just given you some, don't use all of this though, okay? Because we're still going to use that paper. So, all right, so I want you to play with this just a little bit, okay, right? Try here these simple cases, okay? We could start with 0, but we already answered that one. So, but that is a possibility here that I allowed. All right. So try drawing a few lines there, and just count the number of regions that you get. Make sure you draw them in general position, though. Okay. Now look. So our set, I don't think I explicitly said the set, we're going to call this set L, and that's the set of regions formed by the lines, right? Okay, and so we're interested in counting that set. Of course, that set is non-empty, so that's not an interesting question in this case, right? Is L non-empty? You obviously get some regions, right? So here we actually do want to count how many regions there are, okay? See if y'all can get me an answer really quickly to those 4 cases. It's just a matter of drawing a few lines and counting, all right? It doesn't really get hard until you get up to 4, but that's pretty easy also. The only thing hard is making sure you count the regions properly, so you might want to number them just to make sure that you get them counted right. We'll make a little table here. So already filled that one in. Okay, so that we don't run out of time, let's see if we've got some answers here. So if n equals 0, we only have one region, right? That is the plane. Okay, so that one's trivial. What about if n is equal to 1? So if you draw one line, then how many regions is that going to divide the plane into? 2, right? Okay, so that's pretty clear, right? Just breaks it in half, correct? Now, here's where it gets a little bit more interesting. What about when n is 2? This is not too hard, but remember, they're not parallel lines, okay? So that's important because the answer changes. So not parallel lines because these lines are in general position. So how many do you get here? 4, right? Okay, so that's pretty obvious, right? You're going to get 4 regions there. If they were parallel, though, you would only get 3. Okay, so so it's important that we specify that they not be parallel. All right, here's where things get harder. All right, so how many when n is 3? Did we get different answers here, or did everyone get the same answer? 7? Did everyone come up with 7? Yeah. Okay, so I think that's right there. The answer is 7. That's what I calculate. And, oh, wow, what about with 4? Did anybody get a dispute there? So 11? Okay. All right, so we'll go with that. Let's keep those values in mind because we want to come up with a formula, right? We want to be able to count the size of this set in general if I specify any value for n, and since we counted these by hand, right, by sort of exhaustion, we want to test our formula with these values. So let's keep those in mind. All right, so here's what our goal is here, okay? We actually want to count this for any number of lines, okay? All right, so let's let L sub k, right, be the size of this set. I'm going to let L sub k be the size of this set, right, the number of regions formed, right, when the number of lines is k, okay? So when we draw k lines, that will be the number. L sub k will be the number of regions that's formed. All right. So here's what we're going to look for to solve this problem. And this is a very typical method for solving counting problems. It's a little bit advanced, so it's not the first method that we're going to study starting soon here for solving counting problems, but it is a common one. All right. So here's what I'd like to find. Okay, see if you can find a relationship. Okay, see if you can find a relationship there between the number of regions that you get if you have k lines. Okay, with the number of regions that you get when you have one fewer line. Okay, one fewer line. All right, now, here's the way I suggest you think about this. So we'll leave this till next time, okay? But you may want to ponder this, okay? Imagine already that you've got some lines there drawn on the plane, okay? All right, so we'll just say it's k minus 1, but you can just scribble this and draw sort of any number of lines on the plane in general position. And then think about what happens when you add the next line, okay? So when you add the next line to the ones that are already there, okay, how many more regions do you get, okay? You're not going to, by the way, take away regions, right? When you add a line, you have to get more, all right? So when you add the next line already, if you have a certain number of lines, and then you add one more, you know, across all of those pre-existing lines, how many regions get created, all right? How many regions get created? Remember, these are in general position, so when you add your next line, right, remember it's not going to be parallel to any of the pre-existing ones, right? Not going to be parallel to any of the pre-existing ones. Since it's not parallel to any of the pre-existing ones, what does that mean? It's going to have to cross every single one of them, right? Okay? It's going to cross every single one of them, and since it's in general position, it's not going to cross 2 at the same time, right? Okay? It's not going to cross 2 of them at the same time, okay? So it crosses all the previous lines in distinct points, okay? In distinct points, all right? See if that information, right, can give you an idea of how many new regions you create when you add one additional line there, okay, in your picture, all right? Okay, sort of thinking about that picture will give us that relationship between the number of lines we have, the number of regions we have when we draw k minus 1 lines to the number of regions we get when we add one new line. Okay. All right, so we'll finish solving this problem next time. Now, let's go back to our homework. All right. So this is our kind of third big example of kind of settings for combinatorial problems. We have one more that we'll get to talk about next time. It's going to take a little bit of time but it's kind of fun. It's combinatorial games. Okay. So games are another common setting for combinatorial problems. All right. And but there are particular types of games which are known as combinatorial games. All right, not surprisingly. But combinatorial games are quite familiar to you. Combinatorial games are two-player games that do not involve chance, okay? Right, okay? So they are not games of chance, all right? So they don't involve rolling the die or drawing a card from a deck or something that involves a random occurrence, right, okay? So famous examples of and so many games that you know of are indeed combinatorial games. But there are lots of varieties of combinatorial games, I should mention. So checkers, for instance, is a combinatorial game, right? That is not it's a two-player game, right? And it does not involve a chance. Chess is another famous example of a combinatorial game, okay? Tic-tac-toe is a combinatorial game. So almost any two-player game, there are some exceptions, but almost any two-player game that does not involve random occurrence is a combinatorial game. Okay, and there are many classic, famous, well-known combinatorial games like NIM. Do y'all know the game of NIM? Okay. Oh, y'all don't know NIM? All right. So, but you probably know Go, right? Okay. All right, so that is kind of a very classical combinatorial game. All right, but the game. So these are also really good settings for combinatorial questions. Okay, the classic one being, does a particular player in this game have a winning strategy? All right. So, are there a set of a method of making moves that a particular player can use so that that player is guaranteed to win the game? Okay. All right. That's frequently the question that's asked about combinatorial games. So we're going to play some combinatorial games next time, and see if you can not just win them, but come up with a winning strategy. All right. Let's see. So we have time to at least bring up maybe one question here. All right, from our homework. So let me switch back to the document camera. We talked a little bit last time about this problem, which is a really good problem, but a hard problem. All right, so that's really one to ponder over. Let me give you a hint on this one that can maybe help you think about the problem. So this is a very common strategy for problem solving that you're already familiar with. It's not just for combinatorics, but in general for problem solving. Start with some simple small cases, all right, okay? And think about what the small cases are telling you. So in this problem, we want a chessboard, but the dimensions have to be odd. Both rows and columns have to be odd, right? Okay. And remember, we're going to color in the usual way, right? A chessboard, the squares white and black, and then we're going to take out a white square. And what we want to demonstrate then is that chessboard can be covered by dominoes, right? Okay, so there's the problem. But start with some easy cases. In particular, start with one row, okay, right? And then any number of columns, but the number of columns would have to be odd, okay? So start with just one row and an odd number of columns. And then, of course, you've got to color the squares white and black, right? And then remove one of the white squares and see if in that case you can convince yourself there has to be a covering. And then go up just one order of magnitude. So try what would be after 1 by any number of odd columns. What would be the next? What now? Now, 1 by 3 is still one row, right? Okay. So I said, Shelby, start with one row and any odd number of columns. Okay. All right. See if you get, yeah. So then go up to 3 rows, right? Okay. And the smallest case there would be 3 by 3. Okay. Not 3 by 1 because that was essentially the same as 1 by 3, right? Okay. So try 3 by 3. That is very informative. All right. So the 3 by 3 case, I think, is very informative as to, in general, how you might solve this problem. Okay, so try 3 by 3, see if you can convince yourself, then go up to 3 by 5, right, and see if you can use your idea from 3 by 3 to help you with 3 by 5, okay? Then you might go on to 3 by 7, and then by that point you might have a general idea of you know, how things might be working here. But after 3 would be 5, so see if you can do 5 by 5. If you can do 5 by 5, you're in pretty good shape, I think, okay? That you might be able to figure out, all right? So that would be my clue on this problem, all right? Okay, I think this one I probably don't need to give you a clue on there, but just remember you're traveling through white and black squares, okay? Remember you're traveling through white and black squares, and since you're moving from one square to an adjacent square in this tour of the chessboard, remember you're going to have to alternate white and black squares, right? Okay, in this tour. So keep that in mind. All right. This is the one that I wanted to. This is the one that I really wanted to mention. Okay. So 4A here. Look. We're going to just work with a 2 by n chessboard, right? Okay. So that's going to have a perfect cover for any choice of the number of columns, okay? Because we're fixing the number of rows at 2. Remember, what were we going to show in our first problem here? I think we solved this last time, right? If you have an m by n chessboard, right, and one of these is even, right, one of the dimensions is even, then you're guaranteed to have a cover by dominoes, correct? So here, since we're only working with 2 by n chessboards, number of rows is 2, the number of columns can be anything, then we're guaranteed we're going to have a perfect cover, right, because the number of rows is even. Okay, so we definitely have a perfect cover there. What we're trying to do there is count, though, how many perfect covers we have, right? So that's what these values represent. So f of 1 would be the number of perfect covers if you have 2 rows and 1 column. F of 2 would be the number of perfect colors if you have 2 rows and 2 columns, correct? Okay, and what they're asking for there is see if you can find a simple relationship, right, between these values. All right, let me give you what may be a clue here. Okay. All right, so you've got 2 rows, right? Okay, and then any number of columns. All right, and we're thinking about how many ways can we cover that with dominoes. There's lots of them, right? So there's clearly lots of them. So it's not a trivial counting problem, correct? But let's imagine. So we've got 2 rows here, and then these columns. So here we would be trying to solve this is 2 rows and 5 columns. So here, if we count all of those coverings, that would be what in this problem they're referring to as f of 5. Am I saying that right? Okay. F of 5 is the number of coverings for that particular chessboard. Now look, if you get a perfect covering for this chessboard, think about what's going to happen here at the end. Okay. So think about these squares over here on the far right-hand side. Okay, how can we fit dominoes into those squares? Okay, well, one way you could do that, right, is to put one domino, right, okay, vertically covering the last column, correct? I mean, that's conceivable, right, that you could have a domino covering the last column. And then you may have, I don't know, some other arrangement of dominoes, right, in the first 4 columns, correct, right? Okay. All right, now look, So let's imagine that we've got this domino vertically in the last column. So let's sort of ignore that, and let's think about how many ways we can fit in dominoes in to cover the first 4 columns, correct? All right. Well, how many ways can we do that? Well, I don't know, but the book refers to that by some value. What does the book call the number of ways you can cover those first 4 columns with dominoes? What? F of 4, right, okay, all right. So if you're counting the ways to cover the 5 columns, right, it would be, right, the number of ways you can cover the 4 columns, right, with the dominoes, and then plus having this domino vertically at the end, okay? So you know F of 5 is going to include F of 4, right, okay, plus that vertical domino at the end, correct? Now, however, to cover the end here, you do not necessarily have to have a single domino covering the last column. What's the other way of covering here at the end? You could have them going horizontally, right? So you may have one horizontal here. But if you have one horizontal here, then what's got to happen below that? You've got to have horizontal there also, correct? Okay? All right, so that's it. I think that's the only way to cover those columns at the end, right? You may have this vertical one at the very end, or you may have 2 like this, right, stacked horizontally. Well, if you sort of ignore those, then how many columns do you have left? 3, okay? But how many ways can you cover those 3 columns? Well, I don't know, but the book gives that a name, right? What? F of 3, right, okay? So we know that F of 5, I think, is going to be the number of ways of covering the 4 columns, plus a vertical one at the end, right? Plus the number of ways of covering 3 columns, plus the 2 horizontal ones at the end, right, okay? That's what I think F of 5 is going to be, right? Y'all see that reasoning there? So, see here, that's a relationship there. We have F of 5 calculated in terms of what? 3 and 4, okay? All right, now how does that help us? Well, I think that helps us because 3 is probably easy to calculate, correct? What about 4? It's got to be easier than F of 5, right? Okay, so see that relationship, right, there? I think by the same reasoning, right, we could assume what? F of 6 is going to be what? F of 5 plus F of 4, and so on and so forth, okay? This type of scheme for counting is called a recurrence relation, and this is going to be a very useful idea for us when we're trying to count sets a little bit later in the course. Okay, well, I ran over, but not too bad, all right? So y'all still aren't stopping me, but